This video will provide the keys on how to solve the n queens problem. We want to set all the queens so that they don't attack each other, n queens. So basically, we cannot apply brute force because if we would like to check all the possible combinations, that will require a lot of time, more than 1 year. So we would like to solve this with backtracking, in which basically we explore different solutions and we are going forward and backward, changing different possible solutions, but we have to be very careful on how we set the rules so that we explore only the necessary cells. So for this, the first thing that we have to ask ourselves is how do we encode the solution? In backtracking, normally you encode the solution like a vector of numbers, but it can be other options. Here, how we can encode our solution as a vector? Okay, first thing that we have to know is that there will not be more than one king for row, because, for example, if there is one queen here, then you cannot place any other queen in the same row. So as basically we can encode as the number, the columns in which each queen there is. So for example, we are going to encode this as an array or indicating what is the position of each queen in each row. For example, if we get started counting on 0, as we normally do in computer science and vectors, let's say for the row 0, the queen, for example, this part of the solution, the queen will be on the position 0, which is the column 0. The second queen will be on the position 2, because you start counting on 0, 0, 1, and 2. And the next one in the 0, 1, 2, 3, 4. So for example, we are going to actually encode the solution as an array that you can imagine here, in which indicates the position, the column of each queen for each row. In this way, we can represent the solution as an array of just size n. In this case, the common size of 8, it will be an array of 8, right? So in order to represent this array, I have programmed this tool visually. I decided to represent as an actual chessboard. So in this way, you can actually see the solution. But behind the curtain, when we are programming the algorithm, this chessboard will be represented just by one array of 8 positions in this case. Okay. So yeah, that's the first thing that we have to know. So with this encoding, we discard all the possible combinations in which there are more than one queen in one row. Okay. Okay, so in the backtracking, we normally go partially from the beginning to the end for the first position. So you basically assign one possible value to the first row, and then you assign a possible value on the second row, and for each one, you call the function recursively for all the cases. So basically, you start doing like try the first position of the queen, then you try all the possibilities, which again will try all the possibilities and all the possibilities. So basically, you will start placing queens until there is no possible solution, and then you go backwards. So when you finish all the possible solutions and starting by the queen on the first column for the first row, then you will place the queen on the second column, and then you will try again all the algorithm. And basically, as it's recursively, it goes in the exploration in depth, meaning that you first go forward, going all the possible solution until you find to a dead end in which you cannot continue, and then you go backwards. This is why the backtracking is called backtracking, because it goes backward. Okay, so yeah, so basically in this possible solution, you will start with the queen in all the first column, then for the last one you will try the second column, then the third column, and so on. But again, this will require too much time, even if we have reduced all the complexity because of the columns, then it will be 8 elevated to 8. So yeah, again, it's not the most, we have to improve this. So the next thing that we would like to see is that if we place one queen in a way that it attacks another one, then we don't need to go forward, right? So yeah, we could check if there is any column attack and so on. In order to be even more efficient, what we are going to have, and we have here, is to have an array of all the columns that are attacked. So in this way, before the recursive call, when we place one queen, we set the column as attack. For example, if we are in this partial solution, then there are 3 columns attack, you see here. So these are set to true, And whenever you go backwards, you establish again for false. So right now, for example, in the partial solution that we are, then we know for sure that we cannot place the next queen in any of these columns, right? So you can only place here, 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 considering the columns, right? So we go next, the next one will not be in any of the columns. Okay, that now it's improving, right? But we can apply the same concept for the diagonals. Okay, so we cannot place here, but we can also we could not have also placed it here because it will be attacking this one on diagonals. So basically, we can have an array indicating all the diagonals that are already attacked. Let me maximize this. All the diagonals that are attacked, and we have two kinds of diagonals. We have increasing diagonals and we have decreasing diagonals. Okay, so for example, this increasing diagonal, this one will be this true corresponds to this one, which is attack. The second one will correspond to this next diagonal, which is not attack, and the next one is not attack, and the next one is attack. You see, this one is correspond to this diagonal. So we can have also an array of all the diagonals attack. We do the same for the decreasing diagonals, right? So basically this one, and let me zoom a little more. This decreasing diagonal corresponds, this decreasing diagonal corresponds to this one, which is not empty, this one to this one, and we go like this. How do we represent this? Okay, it's basically, it's either some sum or subtraction, but it's difficult to think about the first time. For example, in the increasing diagonals, we can assume the position of the row and the position of the column. So every time that we place a queen, we calculate the sum of both of them, and we establish to true the increasing diagonal. So for example, this one, which is 0 plus and 0, 0 plus 0 is 0, so the increasing diagonal is 0. This one, which is 0 and 2, is 0 plus 2, so the position 0, 1, 2 is set to true. And for the decreasing diagonals, it's something similar, but we have actually to subtract one value from another. So in this way, when you are here is one of the two dimensions subtracted by the other one. So basically, then it actually goes to 0, because you see. So there is another equation in which you calculate the decreasing diagonals. Okay. So right now, having this in mind, then we can continue forward, and you see we can now, when we place the diagonals, you see we have all these columns attacks, all these increasing diagonals attack, and we continue. But sometimes, for example, there is no possible solution to continue forward because all of these positions either are in a column, in an increasing diagonal or a decreasing diagonal. So this makes us to avoid to going forward. Key is the depth in which you are assigning. In other words, is the row in which you are setting the next queen. So right now there is no other possibility. So we check with this and we go forward, and you see there was no possibility. Then it got backwards to the row 4. There was no other possibility, and now we got to the 5, and now there is no other possibility. So we go to the 4 and we try a different thing. And if we go forward in this recursive call, then we go again in the exploration, like setting more queens until there is no possible solution. And when there is no possible solution, we go backwards to the next level and we try the next possibility. And if not possible, we get backwards until there is another possibility. So it's like we're exploring all the possible solutions until there is no possibility more. But there is no other good possibility, partial solution. But as you can see, it's much more efficient because we, for example, the calculation of columns, increasing diagonals and decreasing diagonals, they are already calculated there. So they are, let's say, in constant time, we can check if it's already attacked. And there are actually no many positions and no many variations. So it's actually in a reasonable amount of time. So for example, if we go forward, then you can see how, in this case, if we go to the 7th level, but there was no 8 queens, so we go backwards. As you can see, it's not so easy, but if we repeat this algorithm, this is like going forward in the backtracking algorithm, then you eventually will find one possible solution, right? So here we are running what the algorithm runs, right? And you see that all the columns and diagonals are updated until finally some eventual time we will get to the actual solution, right? And you can see how we got to the actual solution. And we keep forwards, and here you got it. There is an actual solution. You see, the time is very reasonable because we have actually going step by less than a second by ourselves. So if we run the algorithm through, then we will detect the solution for the problems very fast. So you see, now we got to a solution. Just to mention, this works for any size, so this interactive tool. So for example, if you want to try on 10, then it's the same, right? So you can try all the possible solutions. Okay, so now you see how you can how the algorithm works, how the solution works, what are the key for actually implementing it, even though we have not programmed it, but you can see how are the keys for solving this problem. So in this way, you are much well prepared for solving the Encoding problem. Okay, thank you for watching. Bye.